Alright guys, so we are picking up chapter 11. We are on slide 47. At the end of the last PowerPoint, I showed a problem where we're drawing the phase diagram and heating curve for iodine. So if you want to refer back to that, again, it's slide 47 in the PowerPoint. So it gives us all the information we need. We're drawing two graphs, so I kind of went ahead and set up the beginning of them. First of all, the phase diagram. You need to know that the axes are pressure and temperature on a phase diagram. I started out with the point, I'm drawing kind of a Y shape. So the triple point is kind of the center of the Y. I went ahead and said, okay, the triple point was given to be 113.4 degrees Celsius. And then the pressure was given to be 92.3 torr. Now the other pressure measurement was in atmospheres. So I went ahead and converted 92.3 torr. If you divide that by 760, that gives you 0.12 atmospheres. So that's my triple point, 0.12 atmospheres and 113.4 degrees Celsius. I know that from there, I'm going to make the Y shape. So I'm going to kind of have my section that comes down. That separates the solid from the gas. My solid to liquid lines can be fairly vertical. So going to be something like that. And then my liquid gas line is going to be more of a sweeping curve. It's going to go out like that. Okay, so just general look, that's what a phase diagram tends to look like. All right, now my other points I can label. If it gives me the normal boiling point and the normal freezing point, that's going to be 1 atmosphere. So if I go up a little bit, 1 atmosphere. I'm going to be able to label if I go across right there, that's going to be where my heating curve is going to come from in a little bit. But the point right there, that's going to be the melting point. And then the point right here is going to be the boiling point. Okay, now if I go down, my melting point, it tells me the melting point of iodine is 113.4. Now, this one's the triple point was 113.4, the melting point is 113.5. So it's going to be slightly to the right of that one. So I'm just going to come straight down and say it's like right beside it, right there. So 113.4 is on the left, 113.5 is on the right. That's the one that lines up with my melting point. All right, then my boiling point, if I come down from there, my boiling point given was 184.3, so I can label that one, 184.3 degrees Celsius. And then finally, it gives me the critical point way up here. And again, I have to have room on my axes. So the temperature coming down is going to be 512 degrees Celsius. Now, obviously, my scale is not fully consistent here. Again, if you were asked to do this on a test, we would be pretty reasonable that you just have to do the best you can with that. But there should be a larger gap between 184 and 512 based on how it started. But don't worry about that too much. And then pressure-wise, the critical point pressure is 112 atmospheres. Again, that should be much higher. But I'm just going to draw my dotted line there to 112 atmospheres. Okay, so generally, everything on that side, that is my phase diagram for iodine with the information that was given. All right, so then it asked me, what will the normal heating curve look like? Well, again, if they gave me the melting point and boiling point in the information, but even if they didn't, if I have a good phase diagram, I go to 1 atmosphere on the pressure scale, I come straight across and see whenever I hit the solid liquid line on that horizontal, that would be my melting point. And then when I hit the liquid gas line, that's my boiling point. So I can get that information from my phase diagram, although it was already given to me separately. So on my heating curve, again, temperature versus heat added. Sometimes they'll just say it's over the time of heating it, it's time on this axis. Either way is okay. But my melting point is the first horizontal. That's going to be my 113.5 degrees Celsius. And then my boiling point up here is going to be my 184.3 degrees Celsius. So again, on the screen, I'm not sure if you can see all the numbers clearly, but hopefully you got it as I said it out loud. So that's what my heating curve looks like. I should really, if I ask you to label one, you ought to have solid, liquid, gas, melting, and boiling. Again, if we ask you to label the heating curve, you want all those parts labeled clearly. All right, so that's it for that. Now let's go back to our PowerPoint. So heating curves. I told you that for most substances, you just have the three phases, solid, liquid, and gas. You get the Y shape, and that's pretty much it. I don't want you to think that that's always the case, though. You know, anytime we teach you something in chemistry, there are almost always exceptions that we need to be aware of. An exception on the phase diagram, if you look at the phase diagram of sulfur, it's much more complicated than what we saw before. The reason for that is sulfur actually has two different solid forms that can exist based on different pressure and temperature. Sulfur can exist in the first solid form. This section right here is called rhombic. And then the second one in this little section right here is called monoclinic. So basically, at a given pressure, normal pressure, sulfur has a solid form, and then if you heat it up slowly, the structure will shift into another form, and it'll probably look different. I don't actually know what the two forms of sulfur look like, but they probably look significantly different as it shifts through. Then if you keep heating it up, it will actually melt and go into a liquid phase, and then if you keep heating it up, it would go into a gaseous phase. So quick question, if you drew a heating curve for sulfur, how would it be different from water? Okay, if you thought about it for a second, hopefully what you came up with is that instead of a water heating curve would have 5 segments, where 2 of them are phase changes. This one, if you drew it, you would have 7 segments. You'd heat up the rhombic phase, and then you'd have to do a phase change to the monoclinic. So that's a diagonal and then a flat. Then in the monoclinic, you have to heat it up, which is a diagonal, and then you have to melt that into the liquid. That's a horizontal. Then you have to warm the liquid all the way up until here, that's a diagonal. Then you have to boil it, that's a horizontal, and then you can heat up the gaseous phase. So there'd be 4 diagonals and 3 horizontal phase changes that could occur. Okay? Now that might seem kind of weird, but another substance that has 2 solid phases is carbon. Carbon can exist as graphite. It can also exist as a diamond. Okay? Actually, the difference between them is pressure-based. Graphite would be, diamond would be up at the top, where high pressure makes carbon exist in diamond. And then at a lower pressure, you get graphite. Okay? So there are lots of variations that we can see. You don't need to know any of them by heart. Just be aware that most phase diagrams have the Y shape, but there are substances that don't. All right, so next topic. We are getting close to the end of the chapter. Vapor pressure. So whenever we deal with liquids, there is always the potential for any liquid that some of it can evaporate and go into the gaseous state, and not just at the boiling point. All right, evaporation is when a liquid turns to a gas below the boiling point. So imagine that if I have a bowl of water on the counter and I just leave it sitting there for a week. When I come back, there probably won't be any water left. And what happens is, in a bowl of water, most of the molecules do not have enough energy to be vaporized. But the energy of particles is actually a range. Again, we'll see the MaxwellBoltzmann distribution later. Some molecules in a sample will have more energy, some will have less energy. We usually focus on the average amount of energy of the particles. Okay, so liquid water at 25 degrees Celsius, the average molecule has enough energy to be in the liquid form. But you'll have a few molecules that might somehow obtain enough energy to escape. If it's a bowl of water that's open, then eventually a few molecules escape, and then if you wait a while, a few more will escape, and if you wait a little while longer, then more and more and more will escape, and they all float away, and eventually you're left with an empty bowl. All right? Now, what if it's a closed container, though? So again, looking at the picture, in a closed container, what happens is you put a liquid into the sample, a few molecules escape and start flying around, and they bounce off the walls and all this kind of stuff. And when gaseous particles are bouncing off the walls, it creates pressure. So there's a certain amount of pressure that can exist based on the vapor in the container. Now, at first, when you put the liquid in there, if above it there's no air, so it's a vacuum, as molecules escape, the pressure is going to increase. But eventually it gets to the point where as molecules escape, some of the ones that are up above the liquid, they're going to crash back down to the surface, and eventually they're going to balance each other out. The number of molecules escaping and the number of molecules crashing back down are going to equal each other, and at that point the pressure is going to stabilize, and that's going to be what we call the vapor pressure of the liquid. It does depend on temperature. For a bowl of water, there's a certain amount of vapor that can escape if it's at 25 degrees or at 50 degrees or at 90 degrees. And we know that, like with water, if you're heating up a pot of water, the closer you get to the boiling point, the more steam you see coming off the surface. So the vapor pressure does increase with temperature. All right? So once it reaches the point where the number of molecules escaping and the number of molecules crashing back down, once they kind of equalize each other, again, in chapter 15 this semester is all about equilibrium. So equilibrium is when two processes that are competing with each other, they balance each other out. And then the word dynamic, what that means is, it's not that they balance each other and then stop. Actually, they get to the point where both processes are still happening. Molecules are leaving the liquid, molecules are crashing back down. So the system is always changing, but yet the two processes are moving at the same speed. So it's balanced even while things change. The word dynamic refers to ever-changing. So I referred to the Maxwell-Boltzmann distribution. This is a key part of this concept where basically this graph demonstrates the range of energy that the molecules could have at a certain temperature. So if I focus on the blue curve, essentially at a temperature, let's just say it's 25 degrees Celsius, okay? At 25 degrees Celsius, the average molecules, if I look at, like, so on the y-axis represents the fraction of the molecules that have a certain amount of energy. So the most molecules, the highest fraction right here, if I come down, there's a certain amount of energy that the average molecule has. It'd be around right here. Okay, so this is how much energy the most molecules have. But there are going to be a few molecules, a smaller fraction, that have less energy. And there's going to be a few molecules that have more energy. Okay, now this graph is going to come up several times this semester, but essentially, whether it's a reaction that's occurring or a physical change, like a phase change, we would say that there's a certain amount of energy that's required for that process to occur. So if we're talking about vaporization, in liquid water at 25 degrees Celsius, most of the molecules are below that threshold to escape into the vapor. These molecules over here, they have enough energy that they can escape the liquid and fly away in the gaseous form. So most of the molecules are over here underneath that level. There's only a small fraction of the molecules that are above that level. That fraction is going to represent the molecules that escape into the vapor and create vapor pressure. So the bigger that fraction gets, the more vapor there is. All right, so for water at 25 degrees Celsius, the blue line, that fraction is pretty small. But let's just say I raise the temperature. So now at 50 degrees Celsius, that's my red line. What happens to the distribution? Well, it gets a little wider because at a higher temperature, there's going to be more of a range of energies. The average instead of the most molecules having this much energy, it shifts to the right. So the average energy of the particles is going to increase, which we said the temperature goes up. So that's more energy. So the whole curve shifts to the right and gets a little bit wider. I'm still going to have molecules that have very little energy, but the number of molecules that are above the threshold, now my fraction over here has gotten bigger. So at a higher temperature, more of the molecules have the energy to escape. So the liquid will have a higher vapor pressure at 50 degrees than it did at 25. Okay? Now, what actually happens is, as you raise the temperature, this is going to shift further and further right. And really, when the average molecules cross over the threshold, that's where the evaporation process is going to really speed up, and that's where it becomes the boiling process. Okay, we're going to define the boiling process in just a minute. So, vapor pressure versus temperature. We know that as the temperature increases, the vapor pressure will increase also. They're directly related, but it is not a linear relationship. If you look at this graph, for water, okay, the blue line right here is water. At low temperature, down near zero, water gives off very little vapor. When I get up to 25 degrees Celsius, it gives off a little bit of vapor, but again, if you look at a bowl of water at room temperature, it's not really giving off a lot of steam or anything. But as you heat it up, what you see is that it advances quickly, and when you get up to like 90 degrees, there's a lot of vapor coming off at that point. That's where you start to see the steaming occur. And then finally, when the temperature gets up to 100, the vapor pressure of water, if you'll notice, it passes by 760 torrs, or 760 millimeters of mercury. And that number should mean something, because in chapter 10, we learned that if a barometer reads 760 millimeters of mercury, that's normal atmospheric pressure. So the definition of the boiling point of a liquid, when the vapor pressure gets to the point where it equals the atmospheric pressure, basically the molecules, they have enough energy to push the atmosphere out of the way, and then lots of molecules all escape at once, and that's when it starts boiling and bubbling and everything. Okay? So the boiling process, the boiling point, is defined to be the temperature at which the vapor pressure equals the atmospheric pressure. So for water, that happens at 100 degrees. Now, what about ethanol? That's this orange line right here. Well, ethanol is a substance that it gives off more vapor. Okay, if you ever have smelled wine or any kind of alcohol, ethanol is drinking alcohol. If you open up a bottle, you can smell ethanol coming out because it gives off a lot of vapor. So, the vapor coming out, as you heat it up, it gets up to 760 at a much lower temperature. It's easier to vaporize ethanol than it is to vaporize water. So if you get to 760 at a lower temperature, that means that ethanol has a lower boiling point. Okay? And then the last one, diethyl ether. Now again, if we refer back to our intermolecular forces, water is very good at hydrogen bonding, strong intermolecular force, so it takes more energy to make the molecules escape from each other, to pull apart, so it has a high boiling point. Ethanol also has hydrogen bonding, but not quite as good as at water, not as good at it as water is, so its boiling point is a little bit lower. And then diethyl ether is actually a polar compound, but it can't do hydrogen bonding. So it just has dipole-dipole forces, which are weaker, so that's why its boiling point is significantly lower. It's only at 34.6. So actually diethyl ether, if you pour it on your hand, it'll start boiling in your hand because the temperature of your body is 37 degrees Celsius. All right? So, now this graph, good demonstration of the relationship between vapor pressure and temperature, but there is an issue. Whenever we make graphs, we really like to model graphs in a relationship that's linear instead of curves. So the next step, a couple guys, Clausius and Clapeyron, basically they took the graph, or they took the relationship between vapor pressure and temperature, they studied it, And they found that they could take those curved graphs and they could convert them into a linear form by manipulating the data. Okay? So what they did, they took the vapor pressures, like they would measure the pressure, they would take the natural log, because these are exponential relationships, they would take the natural log of the vapor pressures and make that be their y-axis. So this is the equation that they are graphing. The equation of a line is always y equals mx plus b. So the y variable in their graph is the natural log of the pressure. The temperature, they converted it into Kelvin, and then they inverted it. So the x variable is actually 1 over the temperature. 1 over t is my x variable. And then the equation line, y equals mx plus b, m is the slope, delta h over r, both those are constant values. If you divide them, that's the slope, although it's got to be negative. So it's negative delta h over r, that's the value of my slope. 1 over t is my x variable, ln of p is my y variable, and then c is just the y-intercept. Okay? By doing that manipulation of the data, they actually converted curved graphs into linear graphs. And then if you make that graph and do a linear fit, the slope of the line is negative delta h over r. So the cool thing about this, if I take a liquid and if I measure the vapor pressure at several temperatures, so I have water at 25 degrees, measure the vapor pressure. Heat it up to 50, measure the vapor pressure. Heat up to 75, measure the vapor pressure. So if I collect all that data, I take the pressures and do the natural log of those values, take the temperature, put it in Kelvin, and then invert it. Then I can build a graph that'll look like this one, do a linear fit, and then from the slope, I can solve for delta H. So I can actually determine the heat of vaporization of a substance by measuring its vapor pressure at a few temperatures. All right? So, here's our graph, again, laying out y equals mx plus b. It tells you y is ln of p, m is negative delta h over r, x is 1 over t, so it kind of breaks all that down, just like I said a minute ago. Those are calculations that you might have to do in your homework, and we might have to do on the test. So make sure you're capable of working your way through that. Now, there is one more version of this calculation. If we measure the vapor pressure at several temperatures, then that's like 5 data points or 10 data points. It's great to graph that, and the slope of the line will give you the delta H value after you do the calculation. But there are times where if we only have 2 data points, with 2 data points, we don't actually, we only measure the vapor pressure at 2 different temperatures. Instead of making a graph and solving for the slope, another way to do it, a little bit simplified, is they derived an equation. And this is what we refer to as the Clausius-Clapeyron equation, where 2 vapor pressures, vapor pressure 1, vapor pressure 2, measured at 2 temperatures, T1 and T2. If we set it up, this equation is derived from this one. If we set it up, we can plug in 2 vapor pressures and 2 temperatures. R is a constant. We can solve for delta H. Okay? So it's a similar process. It's not as good as having more data points and doing a graph. But if you don't have as much time available, or if you're only given 2 data points, we can still go through the calculation. All right, so let's do it. This is an example where we can work through it ourselves and see if we can find the heat of vaporization for a compound called arsine. Okay, so again, what did they do? They measured the vapor pressure of the liquid at 2 different temperatures. If they measure it at 2 different temperatures, then we know this is the equation we need to plug into. All right, now the key is you got to match up your data points. The first vapor pressure goes here, the first temperature goes here. The second vapor pressure they measured goes here, and the temperature that came with it goes here. If we set those up, the value of R, now this is the first time we've seen this. In chapter 10, we learned that R was the universal gas constant. It was 0.0821 liters atmospheres over moles Kelvin. This is a related value, but it's in a different form. This is the R value that's used for thermodynamics. This R is going to be 8.314. Okay, so the R that we plug in here will be 8.314 joules over moles times Kelvin. All right, now, some warnings when we plug all this stuff in. The two vapor pressures can be in any pressure unit you want as long as they match. They can both be in atmospheres, they can both be in torrs, they can both be in millimeters of mercury, or they could be in bars or PSI, any unit of pressure. As long as they match each other, they're going to cancel out because you're dividing them. Okay? R has to be 8.314. And then the two temperatures both have to be in Kelvin. If you forget to change them to Kelvin, the equation doesn't work. It has to be in Kelvin for both temperatures. All right, so if you do that, I'm not going to work this one out yourself, but if you plug in your two pressures and your two temperatures, plug in the value of R, and solve for delta H, you initially will get a value that is 17,700, but that's going to be in joules per mole. A lot of times it's going to want you to put it in kilojoules per mole, so your final answer should be 17.7. So you should plug that in, test it out. This is a common test question that you might have to work, so make sure that you are ready to do it. Also, don't use a graphing calculator. You got to remember that when you come in to take a test, you're going to have to use a basic scientific calculator. So you need to get used to that. It's very different to solve an equation like this one on a graphing calculator versus a scientific calculator. We need to practice with a scientific calculator. All right? Okay, I think we have one more problem. Our video is getting long, but let's finish this one up. So the heat of vaporization for water is 40.67 kilojoules per mole. And that's what's the vapor pressure of water at 25 degrees Celsius. So the key on this one is going to be you have to actually bring in some information from outside the problem. All right, so I'm going to cut off the video. Let's set this one up. So it doesn't really show all the information, but I'm actually going to use the same equation to solve this problem as the one we just used. So the equation was ln of P1 over P2 equals negative delta H of vaporization over R times 1 over T1 minus 1 over T2. Now, you do not need to memorize that equation. It'll be on the formula sheet. The formula sheet that we provide on the day of the test. It's in D2L under the course information and the general materials. So feel free to take a look at that. But this equation is given there. So we just need to know when and how to use it. Okay? Now, on this one, it gave me the heat of vaporization of water. Delta H vaporization is 40.67 kilojoules per mole. And then it asked me, what's the vapor pressure of the water at 25 degrees Celsius? So 25 degrees Celsius will be one of my T values. The vapor pressure at that temperature is going to be my unknown, so that's X. So the weird thing here is it didn't give me the other data point. It didn't give me P2 or T2. So somehow I have to know that. Okay, so if you think about it, how would I know the vapor pressure of a liquid? Well, there's one point that we mentioned a few slides ago where we said at the boiling point of a substance, what is the vapor pressure? And the answer is a substance boils when its vapor pressure is 760 millimeters of mercury, or I could call that 1 atmosphere. Okay, so I'm going to use that as a data point. At 100 degrees Celsius, which I know the boiling point of water is 100 degrees Celsius, the vapor pressure is 1 atmosphere. I'm going to plug those numbers in, okay? And I'm going to make P1 is going to be my unknown, so that's going to be my X, okay? But I can only have one unknown, so everything else I have to plug in. So, ln of X over, now P2, my second data point, I'm going to say that's the boiling point of water at 100 degrees Celsius, the vapor pressure is 1 atmosphere. So P2 is going to be 1 atmosphere. I'm going to plug in a 1 right there, 1 ATM. Now all of that, the ATM, remember I said the pressures have to be in the same units. So if this one's in ATMs, then when I solve for X in a minute, it's going to be in ATMs also. So my vapor pressure is going to come out in atmospheres. All right? Equals negative delta H of vaporization. Well, delta H of vaporization, again, the problem said it was 40.67 kilojoules per mole, but R is going to be 8.314 joules per mole Kelvin. I can't have one of them in kilojoules and the other one in joules. That won't work. So I'm going to convert delta H, instead of 40.67 kilojoules, I'm going to make it 40,670 joules per mole. Okay? On the bottom, R is 8.314 joules per mole Kelvin. And then 1 over T1. So my first data point, the question asked, what's the vapor pressure at 25 degrees Celsius? So those two are a pair. The vapor pressure is the unknown, but T1 should be 25 degrees Celsius, but it has to be in Kelvin. So 25 plus 273 gives me 298. So 298 Kelvin minus the other one, the second data point, that's the one where I use the boiling point of water at 100 degrees Celsius. The vapor pressure is 1 atmosphere. Well, there's the 1 atmosphere. So over here, 100 degrees Celsius in Kelvin is 373. All right. At this point, everything I need is plugged in. The only thing I don't have is X. Well, that's what I'm solving for. So I'm going to talk you through a little bit, but I'm going to let you do this. You should be able to solve everything on the right side of the equation. You should be able to solve that down to a single number. And then to get rid of the ln, I'm going to do the inverse on your scientific calculator. The second function on the ln button is e to the x. Basically, that means they cancel each other out. So once I have simplified this side down to a single number, I'm going to do e to the x to both sides. Well, e to ln, they're going to cancel out. So I'm going to have x over 1 equals, it'll be e to whatever number this is. Okay? Now, if you solve it, again, on the PowerPoint, the answer is 0.036 atmospheres. So you need to be able to work your way through that, get to the answer, and then you're good to go. All right? Now, that is it for Chapter 11. Next slide, our next set of slides will be for Chapter 12.